like right at the top of the hour. So, but with that said, hey, welcome to Fireside Fridays. I'm Chris. I will be your host. This week, we're going to be talking about firewalls. If you want a copy of the slides, they're in the Discord Fire content channel. Please feel free to go help yourself out on that one. So, thank you to all of our wonderful team of companies. And today's just going to be lecture. This is actually kind of a two-parter because there's just too much content around firewalls to fit into one week. So this week, I'm going to kind of talk about firewalls in general. Next week, I'm actually going to have you set up some firewalls and do some testing through them. I'll talk more about that when we get towards the end of the day. So when you talk about firewalls, when you talk about controlling traffic, they tend to fall into two categories. We have packet filters and we have proxies. And they're very different in the way that they interact with the traffic that's going by. And I'll kind of dig into them deeper as we go through. There are also host-based firewalls. I'm not really going to be covering those today. We've got some host-based security content that's going to be coming up in another month or two. So I'll get back into those at that point there. Typically, host-based firewalls work pretty much like what we're going to discuss with packet filters. The exception being is that some of them actually give you some control over the application that can run as well. Since the software is running on that endpoint, it can not only look at what ports and what types of protocols are going over the wire, but it can look at what applications are actually accessing them. So you could go in and you can say, hey, Chrome can talk to TCP 443, but Firefox can't for whatever reason. So we'll get into those a little bit more. Like I said, a couple of weeks out. But packet filters are basically routers with the ability to control what traffic is allowed to pass through them. So a packet filtering firewall has to be in line, meaning it has to be along the path of where you want to control traffic. If you put it out to the side, it's not necessarily going to do you any good. So it's got to be in the path. And it acts like a router in that it's going to route traffic across it, but it gives you that additional functionality, being able to create rules that describe what things should be allowed to pass across it and which things will not be able to pass across it. So, as the slide says, acts a bit like a traffic cop in that aspect. Proxies, totally different. With a proxy, it's actually interacting directly with the application layer, and it's typically acting like an application that's associated with that protocol. So, for example, if it's a, excuse me, if it's a, if somebody's using a web browser, they may be talking to something they think is a web server, but it's actually just a proxy. And then the proxy will terminate that end of the connection, acting like a server. And then it may turn around and actually act like a web browser client when it talks to the real server on the other side of it. I'll get into those a little bit more as we go through. So when you get into packet filters, you typically have three possibilities in how to interact with that traffic. The first one is permit. That one's pretty straightforward, right? So this is our rule that says, hey, this traffic can go off and do this certain thing. So it can talk to TCP 80, 443, whatever it is we want to go through and create a rule around. Typically, the constraints of the rules are around IPs and port numbers. So I can go in and I can say, hey, anybody who wants to talk to port, 443 can do that, but they can't talk to port, I don't know, UDP 500 or something like that. Drop is the opposite of permit in a way. It's saying, okay, we're not going to let this type of traffic pass through. So I may have a web server that has a web server process running on it and an SSH server process running on it. And I want people on the internet to be able to access the web server, but not access the SSH server. I only want that to be accessible locally. So I might have a rule that permits the web traffic, but doesn't let the SSH traffic get through. Now, drop is the most common way we deal with traffic we don't want to pass through. And technically, it breaks the RFCs. By that, I mean, when you go back to the original RFCs and you look at, what are the acceptable ways to handle traffic, if you don't let something through, you're supposed to return an administratively prohibited error. You can rate limit the response on that if you want to, but you're supposed to send back something that says, hey, the service you're trying to get to, there's a device in the way not letting you get to it. It might be running, might not. That doesn't matter. You're not allowed to access it. So drops aren't supposed to happen. but we do it anyway. There's a misnomer that by dropping traffic, we're stealthing the firewall. I've heard that way too many times. Oh, you drop rules, hide your firewall. No, they don't. We talked about TCP and we talked about how if I try to talk to a TCP port, if the port's open, I get back a SYN ACK. If it's closed, I get back a reset ACK. If it's offline, I get back a host unreachable. I can go through a bunch of different errors I might run into, but the only condition that will cause nothing to come back at all is a firewall. So by dropping things, you're kind of advertising that you have a firewall. It's not stealthing it, but no response is coming back. Reject is the one that we're supposed to be using. And personally, I like using it when I can kind of mess with what comes back. So reject is we're still not going to let it through. But like I said, we're going to send back some sort of response that says, hey, this isn't being permitted to get by. For most firewalls, when you set up a reject rule, for TCP, it'll try and send back a TCP reset, faking and pretending it was actually the host that sent it back. So it'll change the source IP address and that type of thing. For everything else, it'll typically kick back an admin prohibited. Some firewalls, like NetFilter, give you the ability to control what type of reject messages you use. And one of my personal favorites is host unreachable. So if somebody's trying to get to my web server and they're trying to hit any port but the web server port, their tool gets an error message back that says, hey, sorry, that box is offline right now. And a lot of times you can disable scanning by sending back these error codes that pretend that the host is offline when in fact it actually isn't, which is kind of neat. Let's see, drop for traffic, directly send it out a firewall, i.e. a scan. Well, again, Kafka, I'm more of a reject guy. What I found, and now this is going to sound weird, what I have found is that most tools, if I send back a host unreachable, even if it's the source IP address is the actual host, that tends to fool a lot of tools into thinking the host is offline. It's kind of weird to me because, like, if the host tells you, hey, I'm offline right now, that's still looked at as an ICMP host unreachable. Therefore, the host must not be there, just the way that the software tends to get programmed. Now, with that said, some tools like Nmap give you the ability to ignore those. You can tell Nmap, hey, I don't care if it's offline or online, scan the whole damn thing anyway. And, that might circumvent some of these errors that are coming back. At the very least, you should be using reject for anything outbound that you're filtering, because that's going to allow the application that's trying to get out to return faster and not sit there in a hung state waiting for some sort of response to come back. Possibly dumb question, was drop designed to do, if not what we use it for? Well, it was designed to be an option. I think it's a misunderstanding about how the protocol works that led to that mistaken rumor. I think folks felt like, oh, well, if we send nothing back, they have no way of knowing we're here. It's kind of like if you sit there quiet and don't say anything, people might not notice you. And I think they looked at it that way. But when you understand how the protocols actually work, we always try to generate errors when something goes wrong. When errors don't get returned, that is actually a suspect state. Let's see, but responses that speeds up a scan, right? Um, well, maybe. Again, it kind of depends on the scanning mode and the tool you're using. But like I said, if I'm returning back a host unreachable, a lot of tools are going to look at that and say, oh, that host is offline. Okay, I'm not going to bother scanning the rest of the ports. So does it speed up the scanner? Sort of. You're right. It gives up quicker. It doesn't find the actual open ports, but it does give up quicker. Would that speed it up? Yeah, you could argue it does, but it's also going to get back erroneous data. I like to kind of mess with the attackers as much as I can. Anytime I can throw back weird stuff to them, I like to do it, just because they spend so much time making our lives miserable. I don't think we return enough in kind. One of my other favorites is, and again, this is something you can do with NetFilter. You can go in and you can say, hey, anything with a TTL of 5 or less, quietly drop that packet or reject it or whatever. Reject it with a host unreachable. And what that does is that makes that firewall go from looking like one hop to looking like five. So as somebody's trying to trace route into your environment, they'll trace past the router, they'll get to the firewall. The firewall will act like, five hops of, hey, yeah, you still couldn't get to that web server yet. And then you get to the web server, and now it makes your perimeter look different. And, can the attacker figure out it's fake? Maybe. It takes more skill, it takes more time. Again, anytime we can do something to make their lives more difficult, that's only us stepping up to the game because, as I said, they invest a lot of time in messing with us, and I think we fall flat on that. We don't return the favor enough in kind. All right, so let's talk about the different types of static firewalls, or excuse me, packet filtering firewalls. So the first type of packet filtering firewall is referred to as static. What static does is it pattern matches on a per packet basis. It has no concept of state. What do I mean by state? State is some semblance of a memory of what may have transpired between these two systems before. In other words, with a static packet filter, I can't say, hey, my internal system sent a packet to that web server out on the internet. So I should let the reply back in from that web server out on the internet. It has no way to remember that first packet. So when it receives that reply from that web server, all it has to work with is what's in that packet to decide whether it should actually let it through or not. This becomes problematic because if somebody starts crafting packets, that may allow them to circumvent our firewall rules. So the upside of static, it's very fast, it's very efficient. The downside of it's the most challenging to work with because you end up having to make your firewall look a bit like Swiss cheese. So for example, I said, hey, that web server, needs to be able to send a reply back to that client. So with a static packet filter, what would that rule look like? Well, what that rule would look like is I would have a rule that says, hey, anything coming from the internet that doesn't look like connection establishment, meaning SYN is turned on by itself, go ahead and let that through. Well, that could be a reply from the web server. That could be somebody doing an ACK scan or a FIN scan or some sort of scan where SYN isn't turned on by itself. It could even be like a SYN FIN scan, right? That's still not SYN turned on by itself. So static is fast and efficient, but you end up with a piece of Swiss cheese because it doesn't do a very good job of giving you the flexibility to control the traffic properly. Let's see. Network 6 says, uh, when I think about what Chris learned me in webinars, when you scan stuff is not SYN scanning faster. Um, Usually, yeah, we kind of talked about that when we got into scanning, where you can do a SYN scan, you can do a FIN scan. Technically, SYN scans tend to run a little faster than trying to use some sort of alternate flag combination. So again, static filtering, this is our most rudimentary way of doing packet control. So to kind of give you an example, right? Let's say we were kind of running some tests against a static filter. What would we expect to say? Well, if an unsolicited connection establishment comes in from the internet, it's going to drop that, right? If SYN's turned on by itself, everything else is turned on. If I have a firewall, let's say I have a policy that says, let my internal users go out to the internet, let replies back in, but don't let back in connection establishment. If someone tried to send connection establishment past the firewall is going to actually block that. It'll let, excuse me, sorry, get something stuck in my throat today. If outbound HTTP sessions or HTTPS sessions, it's going to permit those through okay. Where it's going to start falling down, like I said, is anything that looks like a reply coming back, because that could be a legitimate reply. It could be somebody messing with the TCP flags, turning SYN and FIN on at the same time, or only turning on the ACK flag, or only turning on the, FIN flag or whatever. Those are going to be able to punch through our firewall because, again, we got to let all replies through just in case. Unsolicited TCP FIN, yep, that's going to sneak through. Inbound traffic with the source IP address of the internal network spoof may be permitted. What I mean by that is the firewall doesn't automatically know what's internal, what's external. You could fix this with a rule. I could create a rule depending upon the firewall. I could create a rule that says, hey, my internal network address space, if I see that trying to come in from the internet as is and it's listed as the source address, don't let it through. And static could take care of that. I got it in kind of orange here because you could actually know to worry about that and write your own rule to kind of deal with it accordingly. Now, with stateful packet filters, we have the ability to remember earlier packets and make traffic decisions based on that information. So, for example, with a stateful packet filter, I might have a static rule that says let anybody go out to the internet. And I might then go in and say, hey, for any traffic coming from the internet, look at my state table. And if the reply matches something in the state table, let that through. So to give you an example, I send a SYN packet to a web server, right? That matches my outbound rule that says let anybody go out, and that's fine. And then a state table entry gets made that says, okay, Chris's system was at 192.168.1.10, and he was coming from port 1234, and it was going to port 80 and IP address 1.2.3.4. So now if I see 1.2.3.4 responding from port 80 to port 1234 at 192.168.1.10, I know to permit that throw. But if I see any other IP address trying to hit that port on that system, I'm going to go through and drop it. So one of the things that kind of happens with the stateful firewall that a lot of folks miss is that your rules are that you see in your rule base are not necessarily the first thing being processed. Most commercial firewalls will process the state table first, and if they don't see a state table match, then they'll get into actually matching against the rules themselves. And that whole process tends to be kept kind of invisible from you. Now, with that said, if you use something like NetFilter, the firewall that's built into Linux, you get to decide when you want to process that state table. Most people choose to do it first because there's more replies than initial, start a session packets. So that tends to be more efficient. But if for some reason you wanted to make sure that things got filtered out, and not matched against the state table, you could process the state table at any time that you wanted to. So you get a little bit more control with something like that. Well, this is awesome because now that hole we had, we had to make our firewall look like Swiss cheese to let in replies. We don't need to do that anymore, right? All we need to do is define what we want to let through, and the firewall will automatically assume anything we let through, we must want to see the replies coming back, and the state table will take care of that. The exception is ICMP errors, right? So let's say I'm going to port 80 on 1.2.3.4, and I get partway there, and back comes a time exceeded in transit. Well, I said the state table is made up of the source and destination IPs and ports that are talking to each other. That ICMP unreachable isn't going to match any of those state entries. So with a stateful firewall, even though I can let replies back in, I'm still going to have problems with things like ICMP errors. If I try to get to, let's say, UDP port, 123, and that port, let's say DNS port. That's one everybody's familiar with, UDP 53, right? So let's say somebody sends something to UDP port 53 to talk to what they think is a remote DNS server, but that port's closed on that system. What's going to come back is an ICMP port unreachable. Well, again, the state table entry is going to be the source destination IP and port numbers based on UDP. When ICMP comes back, well, that's different. That doesn't match the state table. So our stateful packet filters fix the reply problem, but it still has issues with things like ICMP errors. NAT and PAT rules generally match first, then state table is applied. In In a commercial firewall, that's exactly right. Although I haven't talked about NAT and PAT yet, I'm going to get to that towards the end of the presentation. So, like I said, our limitation here is that related traffic, like that ICMP port unreachable, like that ICMP host unreachable, like that ICMP time exceeded in transit. Those are related. By related, I mean they were caused because of that session, but the packet doesn't match the original session. It's ICMP instead of TCP. It's coming from a different port than, a different IP address versus what the original destination IP address was. Do I care about ICMP? I do, because we kind of end up in a position where we're back to dealing with Swiss cheese again, where we say we're going to let it through all the time and we're not going to let it through at all. It's not as bad as what we were dealing with a static firewall, where we had to let replies back in all the time. And if we didn't do that, our communication sessions would just never work, right? If you let traffic out, but you don't let anything in at all, it's just, you might as well not have an internet connection because you're not letting any of the replies back. The reply is going to be able to make it through. Well, with ICMP errors, your system will still work. It'll just run slower, right? Rather than getting that destination host unreachable error to tell you, hey, don't bother trying that system again, it's going to try again and then double the timeout and try again and double the timeout, try again, so to speak. So things will run slower. They won't run as well if you're not letting through ICMP, but you can at least still be functional. But it'd be nice if we could kind of take care of ICMP as well. So one of the interesting things about related traffic is it's in the payload. We talked about this when we talked about ICMP, right? We said anytime an ICMP error gets generated, the packet that caused that error to get generated is down in the payload. So if our state table could match on information in the payload versus the IP headers, that would help us fix this problem. Well, this is where stateful inspection comes in. So stateful inspection is stateful packet filtering plus the ability to look at pattern match within the application layer and use information there to be able to make good decisions. So again, to go back to this one, right? We originally had a UDP packet that was coming from this upper port number going to port 389. And what came back was a ICMP error message saying, sorry, that port is unreachable. You can't get to it. So if I had a firewall here, right, and I saw the original packet that, came from here and went to their came from here and went to their type of thing, and said, well, I sent a UDP packet, but this is an ICMP coming back with a stateful packet filter, I'm hosed. Because again, I get to let them through all the time and not let them through at all. But with stateful inspection, I can say, hey, anytime you see an ICMP type 3 error, some sort of host unreachable error, don't match the IP headers against the state table, offset into the payload here, look at this value, which is the header that caused that error to take place, and use that information to match against the state table. And if you see a match, let it through. If you don't see a match, don't let it through. Let's see, Chris, on a commercial type firewall, if stateful and if set to pass-through mode, does it still perform stateful inspection? Depends on how they define pass-through mode. That would be a lot. So for some vendors, when they talk about pass-through mode, what they try to do is they try to act more like a bridge than a router, but they're still implementing their firewall code in a normal fashion. But I can't guarantee that every single commercial product is going to work that way. That just seems to be the most common implementation I've seen. So stateful inspection is where we want to be. And not only does it fix things like ICMP, but we have complex protocols like FTP. FTP sets up a command session to TCP port 21. And then when you want to transfer information, it negotiates what ports to use outside of that, right? So TCP 21 is where we'll log in, where we'll send a get command or a put command or that type of thing. But when we actually need to transfer a directory listing or file content, that needs to set up a second channel. That data can't be transmitted through the command channel itself. Well, those data transfer channels, those data sessions, are negotiated on the fly. So we can't really predict what'll get used to be able to set up firewall rules in advance. So with stateful inspection, we can say, hey, this is what an FTP session is. And it's going to negotiate a secondary channel in this session here. Here's how to look for that information. So you can now create a permit rule in order to be able to let that information through. So again, stateful inspection. Now we can get into the payload and we can pattern match on certain values that we go in and we program in. So stateful inspection is implemented on a per application basis. So I might statefully inspect FTP and ICMP errors, but I may not statefully inspect HTTP or echo request, echo reply packets, or SMTP traffic, or DNS traffic, or whatever. So stateful inspection is on a per application basis. It doesn't apply to the firewall in its entirety. So when you're looking at a stateful inspection firewall, one of the things you got to ask the vendor is, what protocols do you statefully inspect? And so long as they inspect at least one of them, like FTP, they can call themselves a stateful inspection firewall. If the application is not statefully inspected, then we fall back on how is the transport handled. The transport is where we get to decide, are we going to handle it in a static format or in a stateful format, right? Is it going to be a stateful packet filter or a static packet filter? So if we can't do stateful inspection, how is that transport handled? So we may say, hey, TCP has flags. We don't need to worry about that too much. So we're just going to do static filters. But if it's UDP, we'll be stateful for UDP packets, but not TCP. So again, this comes down to a vendor implementation. You got to look at how the vendor handles it. If we don't statefully packet filter the transport, it falls back on static. So one of the dirty little secrets in the firewall industry is that when a vendor says we're a stateful inspection firewall, they could statefully inspect one protocol, have static filters for everything else, and they can legitimately call themselves a stateful inspection firewall. Now, some firewalls may do that. They may only do one. Some may do 50. You got to ask the question. And if they're not doing stateful inspection, you got to ask, how are you handling the transport? Is it in a static fashion? Is it in a stateful fashion? Because again, that matters. So it's not uncommon to have a stateful inspection firewall that's actually using static-based rules for a lot of the possible traffic control. They tend to focus on like the TCP, UDP, ICMP stuff, and a lot of the other stuff is just static, right? It's static filters only to deal with, and that's it. No, no. If I'm doing IPsec, I want to be able to say, hey, I only want to permit protocol 50, which is ESP, to this particular address. I don't want to let it pass in every direction, or let it pass outbound from that device. I only want to let it in type of thing. I want that stateful packet filtering control. I don't want to handle it in a static format. So you got to ask the vendor. Now, a lot of times, whoever you're talking to with the vendor has no clue. They have no idea. So how do you figure it out? The way to figure it out, test it. Go in and test it for yourself. I've always been I don't trust the vendor to give me the right answer. I want to test it myself to find out. And over the years doing that, I have been amazed at how much traffic gets passed through. One of the things Checkpoint was well known for. Now, disclosure, I haven't used a Checkpoint firewall in probably over 10 years. So they may have cleaned this up since then. But back in the day, if you created a single rule in a Checkpoint firewall that said one going anywhere, drop it, you could still get ICMP through. You could still get UDP 53 through. There was a bunch of protocols they would still pay, anything that looked like RIP traffic. There was still a bunch of stuff that would get passed. They just wouldn't log it if you had an anyone going anywhere, drop it rule. So I always like when I work with a new vendor product, create one rule, anyone going anywhere, drop it, and now start crafting packets and see, do these actually make it through to the other side? As far as I'm aware, Checkpoint is the only commercial firewall that's fully stateful. I don't think that's a true statement. I know Cisco has been stateful way back to like the PIX days. NetFilter is like NetFilter, in my personal opinion, the free firewall built into Linux fucking blows away Checkpoint. There's so much more I can do with the free firewall built into Linux than you can do with the Checkpoint firewall. The downside is you don't get the pretty GUI. Now, there are some folks that have built a pretty GUI for NetFilter, but it tends to dumb it down to like the Checkpoint level. So yeah, I've mentioned a lot about NetFilter, and we'll actually play around with NetFilter in the webcast next week. We'll go through and we'll kind of look at, how can you create rules in, what do they look like when you start testing them with traffic. This honestly is my favorite firewall. You can't beat the price point. It's built into Linux, but the flexibility on it is just amazing. I can do things like I can say, okay, permit traffic to the web server, but I'm going to rate limit every source IP address so no one IP address can ever DOS that system. And it's just built right in and it's there for free. There's a ton of different expansion modules that have already been pre-built. And quite honestly, it's not that hard to go in and kind of build this stuff for yourself. I mentioned one of the things I like about NetFilter is the ability to customize the reject message. So I find that I actually get a lot of attackers to back off simply by saying, hey, host unreachable. Sorry, that host is offline, even though it's actually not. So you can do a lot of cool things with it. And it is a full stateful inspection firewall. It understands FTP. It understands, last time I looked, it had about a dozen different protocols that it was inspecting. So I keep talking about testing a firewall, testing a firewall. What do I mean by that? Well, what I mean by that is a tool to create packets on one side and a tool to listen for packets on the other. Does it make it through? So, like I said, I like to start simple. Anyone going anywhere, drop it. And now I'll start generating packets on one side, seeing if they make it through to the other. And you can run through a bunch of different TCP ports, bunch of UDP ports. You can try unsolicited ICMP error messages. You can try spoofing the source IP address of the internal network. There's all sorts of things you can go in and try to see, does any of that make it through to the firewall to the other side? And like I said, I've actually been unpleasantly surprised by my results of that type of testing in the past. Source routing is another one that's kind of good to test. Go in and use loose source routing where you say, hey, let's say you've got port 80 open on one system, but you've got port 22 open on another. You can actually do some loose source routing with some and some fragmentation to see if you can initially make it look like you're trying to get to port 80 on the first system, but then change it to port 22 on the other. And does the firewall fall for that? Now, the other thing you get with packet filters is network address translation, or the ability to rewrite information in those packet headers to be able to facilitate the fact that you might be using private addressing internally. So if I send traffic from 192.168.1.10, that's a private address. If I try to, let's say, get to Google, right? Let's say I try to get to one of Google's DNS servers, 4.4.4.4. That packet will make it to that system. But when that system goes to reply, it's a private address. So there may be a number of static routes that point to default routes that are close to the server trying to reply, which means it might make it 3 or 4 hops, but it'll eventually get to a BGP router. And when the BGP router sees it's trying to get to 192.168.1.10, it says, hey, I don't have a route entry for that because it's a private address. You're not allowed to route that in the BGP routing tables. So therefore, I'm going to kick back a host unreachable. Sorry, can't get there from here type of thing. So the server will receive that error. So my packet makes it out with a private address stamped to it. I just don't get the reply back because there's no way to route it back. Well, this is where network address translation comes in. I can go in and I can tell the firewalling device, hey, when my traffic leaves the network, change that source IP address to be something legal. Change it to something else. And there's all sorts of ways you can go in and kind of do this. And I'll kind of talk about some of them as we go through. So there's port forwarding, right? So with port forwarding, what I'm doing, this is more used inbound versus outbound. With port forwarding, I say, okay, anything going to port 80 on the firewall, I'm going to send it to port 80 on the web server, which is located at this IP address right here. So all I'm doing is any traffic that's going to a specific IP port combination, I'm always going to forward it off to some remote host. Many to one NAT. So I can say, hey, all my internal systems, when they go out to the internet, I want them to use, 1.2.3.5. So anybody leaving the network looks that way. Now we have a potential conflict when we do that, which is if I'm rewriting that source IP address, that works great right up until I have two systems trying to communicate at the same time, and they both randomly happen to select the same source port number. Because now if they, so I've got one system using source port 1234, and now I have another system using source port 1234. Well, if the firewall changes the source IP address to always be that same legal IP address and it does it on both, when that reply comes back, it has no way to know which one to send it to. So firewalls have a nice little trick for that. What they do is they'll change the source port. Some firewalls do it all the time automatically. Some firewalls will only change the source port if it absolutely has to because of a conflict like the one I'm talking about now. Again, that comes down to the implementation of the firewall itself. But the idea is now when something comes back to that legal IP address, the firewall says, oh, well, there's actually multiple systems hiding behind that legal IP. What port is it trying to respond to? Oh, that port maps to 192.168.1.25. Okay, I'm going to change the IP address to that IP, and I'll change the destination port back to the port that that system was using. So that's typically how you're going to see many to one NAT implemented. You can also usually do one-to-one NAT, where I go in and say, hey, my web server, 192.168.1.100. Anytime that goes out to the internet, that gets mapped to 1.2.3.6, some legal address. And now anything going to that legal address, that goes to that web server. NAT address pooling. So what I can do with that is I can do one-to-one address translation, but I can do it as a pool and I can rotate through. So if I need to use a fixed IP for an internal system for some reason, I could do that through NAT pooling. So with NAT pooling, I go in and say, okay, everything from 1.2.3.100 to 1.2.3.199 is a pool of legal addresses available for my users to assume when they go out to the internet. And now that'll keep that one-to-one mapping. The challenge there is, what if I have more systems than I have in the pool? Well, that may not work. You may end up with systems that are trying to communicate, and there's no addresses left for them to be able to communicate with. So you don't see address pooling used as often these days because we've gotten a lot stricter with how many legal addresses get added to everybody. Most services updated to work well with NAT. Yeah. So like one of the things we used to run into is IPsec assumed the source and destination port would always be UDP 500. Well, if I'm trying to do many to one NAT and it changes that source port, IPsec would immediately break. So they rewrote the RFCs to have a little bit more flexibility to say, hey, that might be on that port, it might not. DNS used to do the same thing. Back in the day, clients used an upper random port number, but servers always used a source port of 53. So when two servers were talking together, it was going from UDP 53 to UDP 53. Well, again, if I ended up going through NAP, that would break that. So they changed the spec. So I'm not aware of any services that break if you change the source port anymore. I think we've pretty much fixed them all. But if you're using some proprietary protocol and it's not working through NAT for some reason, this is one of the places to check. Packet filter firewall logs. So Firewall logs tend to be fairly minimal, right? They'll tell you source IP, destination IP, source destination port. Here's the time it was seen. Here's what I did to it. And that's about it. Okay, that sounds good. But when did that connection stop? Is there rate limiting in place? Like one of the things I've seen firewalls do is they'll rate limit how often they will log sessions between two different systems if the port numbers stay the same. UDP is a big one for that. A lot of times it'll say, hey, anything that's within the same 30-second window, I'm just going to call that one session and be done with it. Well, maybe it is, maybe it isn't. It depends on the protocol. With DNS, UDP 53, yeah, no, each one of those is going to end up being a unique session. So you may not necessarily get log entries for everything. You may not know when the connection stopped. One of the popular methods of C2 channels these days, or one of the popular implementations, is to just keep the connection and hold it open. And the reason for that is the firewall will log that initial SYN packet, but it doesn't generate a log for anything else going on in that session. So you have no way of knowing, did that connection only last for 100 milliseconds, or has it been running for 100 days? You don't know. A lot of times firewall logs won't give you that information. Um, so it's if you have them, it's definitely good to use them, but they may not necessarily give you all the fidelity that you need. Chris, is stateful inspection the same for IPv6 as IPv4, or is there additional checks for IPv6? Awesome question. So it's handled in a similar fashion, but it's done a little bit differently. So, for example, just to like throw out one example with IPv4, if I don't want to let through IP options, some firewalls would just give me the ability to say, hey, anytime the IP header is bigger than 20 bytes, that's because options are set. And I don't want to support options, so don't let that packet through. And that fixes that problem. Well, with IPv6, we can't do that because IPv6 is a fixed length header. So with IPv6, I need a way to be able to say, hey, the next protocol field, these are the only valid values. Or, don't let it through if it's any of these values, but it's okay to let it through if it's anything else. So the functionality ends up being similar, but the implementation is going to actually end up being very different. That's an awesome question. Okay, so that's packet filters. We also have proxies, and proxies are completely different. With packet filters, we were talking about the kind of acting like a router, the drop in the TTL by one. They might rewrite some information within the TCP IP headers, but it's basically those same headers that's kind of getting passed through. It's just kind of dealing with it the same way a router would. Proxies, completely different animal. Proxies act like a man-in-the-middle attack for all intents and purposes. Think of what a man-in-the-middle attack is. I insert myself between your session, so you think you're talking to some server, you're actually talking to me, and the server thinks it's talking to you, but it's actually talking to me. That's how a proxy works. It injects itself into the middle, but that's actually a feature. So, here's a little design here to kind of give you an idea. Now, it should be obvious for this to work properly, the proxy needs to be application aware. So that's one of the flexibilities you get with packet filters that you don't get with proxies, which is with packet filters, if some new protocol shows up, let's say, protocol 200 is some new fancy protocol that folks want to use. With a packet filter, all I got to do is open up that port. Or excuse me, all I have to do is specify that protocol number. And now I'll have some semblance of control over it. But with a proxy, the proxy needs to be aware of the application. So if something new comes out that the firewall doesn't understand, you may not be able to pass that traffic using a proxy. So it does have some limitations to it. One of the strengths is you have a lot more control and a lot better visibility as to what goes on at the application layer. So, for example, one of the things we're seeing these days is attackers using HTTPS as a command and control channel. And what they'll do is they'll encrypt their data and then they'll wrap TLS around it and send it past your perimeter. And your firewall will look at that and say, oh, it's going to TCP port 443. I'm allowed to let that through. Bang, it goes through. So that C2 is allowed to leak through your firewall. Well, with a proxy, your client, when it talks to the proxy is going to act like a web server. So it's going to expect to see valid HTTP commands coming through. And if it doesn't see them, it says, hey, this is not HTTPS. I'm not going to pass this traffic. And it'll effectively break a lot of potential C2 channels, which is kind of a nice thing. So on the plus side, it needs to be application aware because it's going to implement a better level of security. On the downside, it needs to be application aware. And if it's not aware of your application and how it functions, it's not going to be able to let it through. You're also more likely to run into a problem, right? With a packet filter, I'm just blowing open a hole through TCP/80, TCP/443 in order to be able to support web activity. But with a proxy, it needs to be aware of the application. What if the spec changes, right? What if some new RFC comes out that you can put, and now you can punt, right? So punt is a new HTTP command that we can go through and use. Well, if my proxy doesn't understand what punt means, it isn't going to let that through. So you're more likely to kind of break things if protocol changes take place and the proxy vendor doesn't keep up. So it's a little bit of a balancing act. Proxies can also strip or add headers that the app doesn't understand. Yeah, Kafka, that is absolutely a true statement. So it can change fields. So for example, I'm using a Firefox browser and I go out through a proxy and the proxy is pre-programmed to change it to look like Chrome. Yeah, it can do that. It can change the user agent string as it goes by, no problem. So yeah, there's all sorts of really cool things you can do with proxies. But they tend to require a little more maintenance, again, because they're application aware, again, because they're doing more than packet filters. And I think that's the part a lot of folks miss is they kind of look at packet filter proxy. Well, packet filters tend to just work where proxies tend to be a little bit more problematic. And that while that is a true statement, it's because the packet filters are doing less for you. They're not giving you the same level of security. It also can be argued they're creating a single point of potential security failure, right? If all my users are going out through a proxy and an attacker can get access to that proxy, it's possible they could start sniffing all the data that goes through it. So I got to make sure that box stays locked down. It can also be a single point of performance issues, right? If all my users are talking to the web servers they want to on the internet directly, all I'm doing is simple packet filter pattern matching to decide what do I let through and what don't I, and that's it. Well, if everyone is going through a proxy, that proxy, may be spinning up new processes for each connection going out to each new web server, and that may be problematic. That may exhaust resources on that system. So again, it can potentially be a performance gate. Sometimes it can improve performance. Sometimes it will degrade it. It really comes down to how often are your users going to the same sites, right? Like if everybody in the office visits the same 10 websites out on the internet, yeah, proxy is actually going to speed up their perceived internet speed, right? It's going to seem like the internet is faster to them. But if I have 10 people and they're all going to different sites all the time and none of the two shall meet, yeah, I might feel like the internet's running a little bit slower than it would with packet filter was being used. Would firewall protocol inspection catch C2? Great question. There are vendors that try to do that. The problem is it's signature based, meaning that what they tend to do is they say, hey, if I see this string, right? If I see like the word PowerShell show up in the payload, don't let that through. Well, maybe that's C2, maybe somebody just talking about PowerShell on a forum someplace, who knows, right? So they tend to be a little bit more problematic because they're kind of missing the context of how is that string of characters being used? Is it being executed as a command or is it just part of a sentence? And a lot of times packet filters miss that because it's going in and just doing pattern matching. So can they look for C2? Yeah, they can. But sometimes pattern matching isn't enough to always be able to find it. Don't most proxies, if they reach a traffic limit, the default is to pass the traffic? No, because with a proxy, it has to actually be able to service that application, right? So again, web server proxy, right? It's acting like a web server for my clients. It's acting like a client when it talks to the server. It needs to be able to launch that process. If it can't because it's run out of RAM or CPU time or whatever, there's no way to get to the data on the other side. It needs an application to accept it and then funnel it into the next process in order to be able to push that through. Good question, though, because I have seen that question come up a lot. On my network, I was able to bypass my firewall DNS by switching from Chrome to Firefox. Yeah, I've seen that type of thing before, right? I've seen um, so one of the popular ones I've seen is things like you get a threat intel list that says, hey, these websites on the internet, these are bad. Don't let your users go there. And now when a user tries to get to one of those websites, the packet filtering firewall will try and pattern match on that to see where is it going. And if it sees that fully qualified domain name or IP address, it doesn't let it through. Well, what a lot of folks don't realize is most browsers will accept hex. So if I just put that website in hex characters instead of ASCII characters, I can bypass a lot of those checks. Whereas a proxy is not quite as easily fooled because I could give it hex, but it needs to translate that for the outbound process, and the outbound process will see, hey, this is going someplace it shouldn't be. Now, I've been talking mostly about outbound proxies, but there are a thing called reverse proxies. And with a reverse proxy, what I do is I set up a proxy in front of my web server. One of the nice things about this is these tend to always run faster. Proxies try to store everything in cache. It tries to store everything in active RAM. And as I'm sure we all know, accessing something in RAM is always much faster than trying to access it off of a hard drive. So proxies tend to speed up web servers as well as give you the ability to implement some level of protections. I can go through and I can say, hey, I never want someone to try and write data off to my web server, right? They can get files off it, that's fine, but I don't never want them to try and do the put command. Well, if I have a proxy in the middle, I can tell the proxy, don't pass any put commands, only pass get commands. Hey, I don't even want them doing a head command for whatever reason. So don't let the head command through either. You have that type of control with reverse proxies. So what you see for most websites today, and we do this setup with ours, is we have a web server, but no one ever talks to the web server directly. What they do is they talk to proxies that are part of Cloudflare's network that are spread out all over the world. So you're always accessing a proxy that's a bit more local to you. And again, since proxies cache information, that access is going to be faster. Now, there's a number of different ways I can implement a proxy. I can do it transparently, meaning the end user doesn't know it's there. Typically, however, it tends to be some form of non-transparent, meaning something's changed. Either it's DNS, I've put forwarded off someplace, or the client needs a specific configuration in order to be able to use it. So there's some way of knowing a proxy is in play, but it is possible to do this transparently. And I've seen folks do that. So so for example, I could set up a net filter firewall that is a stateful inspection firewall, but for HTTP and HTTPS traffic, I'm going to use Nginx. And now I can tell the firewall, hey, anytime someone's trying to go anywhere on the internet to port 80 or port 443, send it to that Nginx process that's running on you instead. So you can actually combine these in certain situations as well. If you want to learn more about networking, here's some good ones. NIST has some really good firewall guidelines. I highly recommend going through and checking out that. So next week on Fireside Fridays, we're going to be talking about firewalls again, but we're going to be doing some hands-on testing. So I got a couple of steps for you in case you want to prepare for next week so you can follow along with what I'm doing. So if you're on like a Red Hat flavored distro, change the commands to use here appropriately, using yum instead of apt or apt or whatever the case may be. But all we're doing is, we're doing an update. The three tools we need is, we need ncat and we need hping3. I pull down wget just because, hey, I'm using that in the command here. If you want to use curl, fine, go for it. The only thing I'm pulling down wget for is just to pull down this tarball. If you want to use curl for that instead, go for it. Expand it out. It'll create a directory under your current location called FW. And if you do an LSAL in that directory, you should see something like this. So what I've done is I've automated everything. So what we're going to do is we're going to run a TCP and a UDP listener. And the listen script takes care of setting that up for us. So you can go check out that script and see what's going on in there. Once those ports are open, I can now go in and I can implement some static firewall rules. And now we're going to check different ports to see how does this thing respond while we go through and we run our scan script. Then what we'll do is we'll change it so that we're actually using stateful inspection, and then we'll do a comparison against that and see how it's different. So that firewall testing I was talking about, I'm going to start introducing that next week, doing some hands-on labs, but we're going to do it using only the loopback address just to try and keep things simple, right? If I say, hey, so you need to set up 2 servers with a firewall in the middle, most people aren't going to be able to get that done. But hey, if all you need to do is spin up a Linux box someplace, and it can even be a cloud instance, and that's fine, because we're going to do all this through the loopback interface, that makes this a lot more accessible for anybody. Is Windows native built-in firewall, is that stateful or not? Just wondering. Also, if implemented IP tables with WSL, is that better? Okay, so to the best of my knowledge, the Windows firewall is static, but it also lets you create some definitions around applications. So even though it's not stateful, you get a little bit better control out of it that way. As far as implementing IP tables under WSL, WSL does not control the Windows IP stack. So that will work for that virtual machine. It isn't going to actually protect the Windows interface if you go through and try and do it that way. Cool. And that's it for today. So thank you, folks. I appreciate everybody for sharing your time with us today. Like I said, I got a hard stop. I got another one I got to jump into in just a couple minutes. So we're going to call this done. But if you have any additional questions, the live chat channel is always here. We have a freaking awesome community who's really helpful. So if you have any questions, go ahead and post them there. I will try and keep an eye out for questions, but usually someone else who's smarter than me in certain areas jumps in and answers the questions relatively quickly. So thanks, everybody. Enjoy your weekend, and I will see you here next week. Same bat time, same bat channel.